Hello, welcome to my contribution to Chat Physics Live 2022. My name is Gethyn Jones. On Twitter, I'm known as @EMC squared and all that. And I'm going to be talking about dual coding motion problems. One of the problems we need to address with student understanding of dynamics problems is the problem with the word moving. Quoting from Rosalind Driver's brilliant book, Making Sense of Secondary Science, children's ideas and descriptions of motion tend to be less differentiated than a physicist's. They tend to see objects as either at rest or moving. The period of change, when, for example, an object speeds up from rest to steady speed, or slows down or stops, is less frequently focused on by children. The term acceleration is not commonly used by school-age children prior to its introduction in science lessons. Everyday terms such as going faster are used in ambiguous ways, sometimes referring to the magnitude of the speed of the object, and at other times referring to the speed increasing with time. In other words, the many nuanced ways of thinking about motion that physicists adopt are, for children, packed together in one umbrella term: move. What we need to do as physics teachers, of course, is we need to unpack these terms from the umbrella term. We need to unpack the word move so that students have access to these nuanced ways of thinking about motion. One effective way of doing this is, I think, by using dual coding. Dual coding theory holds that the formation of mental images in tandem with verbal processing is often very helpful for learners. In other words, if we support verbal reasoning with visual representation, then better learning happens. Another way of thinking about what dual coding is represented in this diagram. So first we present a verbal explanation, and that creates a mental representation inside students' working memory. But if we combine that with a visual explanation as well, then it can create an interaction between the two, which can lead to improved performance. The diagram is from Mayer and Sims, 1994, and is backed up by the research that they did. What they say is, instructional methods that promote the formation of all three connections are more likely to promote problem-solving transfer, whereas instructional methods that fail to promote the formation of one or more of these connections are less likely to promote transfer. So, how do I use this when I'm teaching dynamics problems? Well, I use a set of symbols that always mean the same thing. So, for example, displacement is shown as an arrow, and the perpendicular line at the base of the arrow shows the zero of our measurement of displacement. Velocity is also shown as an arrow, but it's very important that it's a different type of arrow to displacement. We need to visually show students that these are different entities. Equally with acceleration, that's shown as a double-headed arrow. And again, it's to indicate to students that acceleration is a different animal that follows different rules to velocity, that you cannot just plug in numbers willy-nilly. You have to treat these entities differently. Time is shown as a clock face, and if we need to indicate that something is zero, very often I draw an arrow and put a cross through it to show that that quantity is 0. Let's see how we would use this dual coding method to help students understand what's going on in a GCSE level question. Well, we start with a diagram and then we just annotate the diagram as we go. So let's put in the time. Notice that with the clock face for the 3.2 seconds, we show the hands of the clock have moved forward a tiny bit. This is to emphasize that this is a later time. We select an arbitrary positive direction, in this case it's left to right, and we put in the initial and final velocities. Now I think it's quite important to show that the initial velocity is 0, so I show that by crossing out the arrow showing the initial velocity, because of course it's impossible to draw an arrow with 0 length. The final velocity is greater because it's a positive acceleration, so we draw that with a longer arrow. So we're just going to indicate that the acceleration is in the direction shown. So using the FIFA system, the formula is the formula for acceleration. We're going to insert the values, and we always do final speed minus initial speed. So in that case, that's 29 minus 0. Going on to the fine-tune stage, we get that the acceleration is that value. So we're going to state it to 2 significant figures, and we're done. Now let's use the dual coding method to help students understand deceleration, which is a frequent sticking point for some students. So we start with a diagram, of course, indicate the positive direction, and let's put in the initial and final velocities. Now, this time, of course, the initial velocity is greater than the final velocity. Let's put in the times, and we've got that on the clock faces. So the acceleration is now in the opposite direction because the speed is decreasing, and so the acceleration will be negative. Let's put it into the FIFA system. So formula for acceleration, insert the values, and notice now we've got the final velocity 16 minus the initial velocity. Let's fine tune and we get this answer, and notice that we get a negative answer. So I think this, in combination with the diagram, shows why very often a negative acceleration is a deceleration. Now let's look at how we can apply this dual coding method to helping students' understanding of stopping distance questions. So the motion of the car can be split into 2 phases. Part where it's traveling at a constant velocity, another part where it's slowing down. And we can indicate this very clearly using the dual coding convention I've outlined previously. So let's look at the times that we know and indicate it with the clock faces there. And the acceleration is of course a negative acceleration since we're starting with a positive velocity and it's slowing down. So let's calculate the change in displacement when the car is traveling at a constant velocity. And we just plug it into S equals Vt and we get an answer of 16.1. Next, we need to work out the change in displacement when it's slowing down. And of course, we can't use S equals Vt here because we don't have a constant V. So we're going to use this expression. And we're going to insert the values, do our calculations. And what we find, of course, is that we get a value of positive 33.9. And 16.1 plus 33.9 equals 50 meters. So by our calculation, the car will just manage to stop before hitting the tree, which of course is good news for the car driver. I think dual coding can help with conceptual understanding as well. and many students struggle with the physics of what happens when a ball is thrown vertically upwards. So we've shown the ball just as it leaves the hand, and it's got a high initial velocity. An instant later, that velocity has decreased because of the negative acceleration due to gravity. An instant after that, it's decreased a little more until eventually the ball reaches its maximum height when its upward velocity is actually 0. Now let's track what happens to the ball on the way down. So we start off with a ball at the top of its flight at its maximum height where the vertical velocity is 0. But it doesn't stay at 0. There's still a constant negative acceleration acting on it. And so what was a 0 velocity will become a negative velocity an instant later. And an instant after that, it's going to be a more negative velocity. And an instant after that, it's going to be an even larger negative velocity. And because we know it's acting under the influence of gravity, it's going to be a constant acceleration. So we expect to see a straight line of best fit as shown on the diagram here. And I believe that if you go through this explanation using dual coding, students are much more likely to develop a sound understanding of what's going on than if you don't. Okay, so far I hope you like the dual coding convention, but a common response is that that's all very nice, but I don't have time to produce all those intricate PowerPoints. Well, you don't have to. For example, what I tend to do is just draw it live, annotate the PowerPoint slide or the Jamboard slide live in the lesson. And I think that works really well. By the way, if you are teaching braking distance, I want to remind students of what reaction time is. This is a brilliant GIF for showing that. It is, of course, a sequence from Star Trek The Next Generation, where the android Lal is struggling a bit with her reaction time. And it always raises, if not a laugh, then at least a smile from students when you show that. Thank you very much for listening, and if you want to hear more from me, I write a blog. It's called physicsteacher.blog. I've also contributed to a couple of books. I wrote the physics chapters in the recent book Cracking Key Concepts in Secondary Science, co-authored with Adam Boxer and Hina Dave. And I also contributed a chapter to the Research Ed Guide to Explicit and Direct Instruction. And of course, you can always find me on Twitter, where my handle is @EMC2 and all that. And I'll just close by giving full references for the publications I used in preparing this talk. The Driver et al. Book is superb. It has had such a positive influence on my teaching over the years, and even though some might call it a bit long in the tooth, it still has brilliant insights into how children actually think about science and many of their preconceptions and misconceptions. And if you want a good theoretical background as to what dual coding is and how it actually works, the Mayer and Sims paper is a really good place to start. Thank you very much, and I hope to see you at Chat Physics 2023. Thanks for listening.